Yeah, no worries. Okay, so we're going to pick up where we left off on Thursday. We were talking about optimization problems. We went through and we did that one for pay. We went through and did a just kind of a classic calculus or algebra problem where we're fencing something in with a little bit of a twist with the two fences on the inside. We ran through just some general guidelines for solving these optimization problems, and we did one that was a little bit interesting where we were trying to minimize the surface area of a can that had to contain a certain amount of volume. And then we're on this problem right here. So this definitely is a real life problem, and you're going to see something like this on the project, project 2, which I need to get ready and get that handed out to you because it's kind of an interesting application here. So here's the situation that we've got. We're in the position of being an engineer working for a drilling company, and they've got a rig that's 12 miles offshore, but it needs to be connected to a refinery that's onshore. And it's set up in such a way that the rig is 12 miles directly away from the coast, and for some reason we've got a coast that's a perfectly straight line. Isn't that nice? And if we went straight to the coast and then went to the oil refinery, that's going to be another 20 miles there. So we're 12 miles out to sea and 20 miles down coast from the refinery. And then here's the situation. Underwater pipe costs $5 million a mile to lay, and land-based pipe is only $3 million a mile to lay. So even though the shortest distance between the two of these is just to go straight there, all of that pipe would be underwater, making it potentially more expensive. Okay? So it says, how far from the oil refinery should the underwater pipe come on shore to minimize the cost? So we know what we're going to be doing here is we're going to need to come up with a cost function so that we can figure out, based on where this pipe lands, how much is it going to cost to lay that pipe so we can get the oil to the refinery. Okay? Now, the way this question is asked, it says, how far from the oil refinery should the pipe come on land? So if we were to draw a line like this, like let's go straight right here, like let's say it's some sort of compromise here. What they would like us to do is figure out what this is right here. Okay? Hold on one second, don't write anything down. Think about the implications of making that the variable x, and then figuring out what all the other quantities are here. This is the water-based pipe, okay? And this is the land-based pipe. So if this is x, I've got to figure out what this is right here. Well, this is a right triangle, so I can figure out what this is in terms of x by doing this. And please don't write this down, 20 minus x. We could then figure this side out using the Pythagorean theorem. Okay? So the way the question is asked might lead us to a function that's a little bit more difficult to deal with. So let's do this. Let's have it come on land right here. We know that we want to find out how far from the refinery we should land, okay? But let's use x for this right here. Because if I use x for this side on the right triangle, then finding an expression for the length of this underwater pipe right here is a heck of a lot easier. It's just the square root of the square of the two legs added together. So that's going to be 144 plus x squared. And how would we represent this right here, the distance from where we come on land to the refinery? 20 minus x. Oops, 20 minus x. Okay? So here's how long the land-based pipe is, and this is how long the underwater pipe is. Okay? To make the problem a little bit easier, let's just talk in terms of millions of dollars. So let's say a $5 mark represents $5 million and a $3 mark represents $3 million. So if we're going to set up our cost function is going to look something like this. Okay? How much underwater pipe do we have multiplied by how much it costs? So that's going to be 5 times the square root of 144 plus x squared. Okay, that's the underwater pipe. That's the cost of the underwater pipe. And then we're going to add that to the cost of the land-based pipe. So that's going to be $3 times 20 minus x. And there's our cost function. Okay, now, what do we want to do with our cost function? We want to minimize this right here. Okay? Now, let's think about this in terms of doing a little bit of calculus on this. It probably would be better if we thought of this as 5 square root 144 plus x squared plus 60 minus x. Or sorry, minus 3x. Distribute that through. That'll be a little bit easier to find the derivative on. Okay, and we should also think about what the real world domain is on this one, because we're going to find the derivative in just a second. We're going to do some calculus on this. But we also want to realize that we might have a max or a min, an extreme value. In this case, the minimum cost might be at one of the endpoints of the domain. So does this have a real world domain, and what is it? What is the smallest we would want x to be? Maddie's got it. 0. Okay? If we let x equal 0, that means it comes straight on land and does straight that 20 miles right along there. That's a 32-mile pipeline. That's the longest pipe we could have, but because it's the shortest distance underwater, it might be the cheapest. Okay? And what's the largest x could be? Largest x could be would be 20. Okay? And that's the case where we go straight here. That's the shortest pipe, but it's also the most expensive pipe altogether. Okay? Every mile we lay is $5 million. Okay? So that could be really expensive. And maybe one of those is the best answer, or maybe something landing in between. We want to figure out what x is. X has got to be a number between 0 and 20, including the endpoints. We're going to check those. Okay? Any questions there? Okay, let's go ahead and find the derivative. So we've got c prime of x is equal to, let's see, this is going to be 5, and then I've got the derivative of a square root. So that's going to be 2, that same square root, 144 plus x squared times the derivative of what's underneath the square root. So that's going to be 2x. Any questions there? Okay. Then this is going to be 0, and then this is going to be minus 3. So if I clean that up just a little bit, I'm going to cancel the 2's, so I get 5x over square root 144 plus x squared minus 3. And what I want to know is, when does that equal 0, and when does that not exist? So let's think about that for just a second. Is there ever a place where this doesn't exist? Not even 12. Because the denominator is 144 plus x squared. We're never in danger of 0. Okay? It's always positive. We're never even in danger of taking a square root of a negative, and certainly not on this interval right here. Okay? So don't have to worry about that right there. All we need to find out is when this derivative equals 0. So the only place that this could have a minimum is at endpoints or where the derivative equals 0. So let's find where the derivative equals 0. I'm going to move the 3 to the other side, so I'm going to have 5x over square root 144 plus x squared equals 3. Really not thrilled about working with that radical in the denominator, so we're going to multiply both sides by that radical. So that's going to give us 5x equals 3, and then square root 144 plus x squared. And then I'm going to square both sides. So again, we're just solving through this. We're just doing a bunch of algebra at this point. So here's what I get. I get 25x squared. I get a 9, and then I get a 144 plus x squared. With me there? Okay, let's be smart about this. We're going to end up dividing in the end anyway, so I'm not going to bother figuring out what that big number is. This is 9x squared, and I'm going to move the 9 to the other side because I've got 2 terms with x squared in it. This is pretty awesome. It's a quadratic, but it's a very easy quadratic to solve. So I'm going to, subtract 9x squared from both sides. And I end up with 16x squared equals 9 times 144. So if I divide by 16, I end up with x equals, let's see, well, let me put an x squared there. Let's see, this goes in there 9 times. So I get 81. So if I finish solving, I get x equals plus or minus 9. Okay, now, those are the answers when we find when the derivative equals 0. Which one of those is the answer we're going to check? Positive 9, okay? Now, if you were an engineer for an oil company and you said x equals negative 9, you're getting fired. okay? Because you're going the wrong way. All right, so we're not going to worry about that one. We're just going to check x equals 9. So here are the things that we need to check. In our cost function, we need to check when x is equal to 0, because that's an endpoint. That would be coming straight on shore. Longest amount of pipe, maybe that saves us money because we did the shortest amount of underwater pipe. Okay, we're going to check x equals 9 because that's where the derivative equals 0, and we know we might have a minimum there. And we're also going to check x equals 20 because that would be straight to the refinery. So we want to find C of 0, we want to find C of 9, and we want to find C of 20. And let's take a look at each one of these. Here's the cost function right here. So if I plug in a 0, I get 5 times the square root of 144 plus 60 minus 3 times 0. So this is So this is going to be 5 times 60 plus 60. Oh, sorry, 5 times 12. Thinking of the answer. 60 plus 60, 120. Okay. Now, what does that mean? Okay, $120 million. So if we come straight on shore, 12 miles of underwater pipe and then 20 miles of land-based pipe, it's going to cost us $20 million. This is a big project. Okay. So let's check and see what we get when we plug in a 9. So this is going to be 5 square root 144 minus, or excuse me, that's a plus, 9 squared plus 60 and then minus 3 times 9. So remember, this is the underwater pipe. So we're going to have more underwater pipe, but we're going to get to subtract off some costs there for that land-based pipe. So let's see, that's going to be square root of 225? So this is going to be 75 plus 60 minus, that was a 9 minus 27, is that right? So what do I end up with there? Okay, so 108 million, okay? So we've already saved some money here. We've saved about $12 million by landing 9 miles downshore from straight on shore. And then the last one right here, so this is going to be 5 times big square root. This is 144 plus 20 squared plus 60 and then minus 3 times, let's see, 3 times 20. So 60 minus, this is 60 minus 60 right there, right? So I end up with 5 times the square root of 144 plus 20 squared. And can somebody tell me what that is? Okay, 116.6? $116.6 million. Okay? All right, so let's run through these scenarios again here for just a second. It's going to cost us $20 million to go straight towards shore and then run 20 miles along shore. Okay, if we land 9 miles, if this right here is 9, if we land right there, it's only going to cost us $108 million. If we go straight there and then use all underwater pipe, it's the shortest distance, okay? But it's a little bit more expensive than that compromise landing somewhere in between, okay? So even though we have to lay more pipe, it's going to be less expensive to go with this route in between here, okay? Now, the answer to the problem says how far from the refinery should you land, okay? 11 miles. 11 miles from the refinery. How much would it cost? Cost $108 million. Now, we've simplified the problem here, but if you worked for a company, and these are real life problems. I have a relative who works for an oil and gas company in Norway, and they figure stuff like this out all the time. Okay? In this hypothetical situation, we would have saved the company $12 million. You think they'd be willing to split it with a smart engineer? No, but they're going to pay you really well. Okay? A couple $100,000 a year wouldn't be too bad if you were saving them millions every time they did something like this. Okay? All right, let's take a look at the next problem. So that one was a real life problem. We're now going to a problem that's completely contrived to make it a fairly familiar situation and see if you can apply some of the stuff that you know from geometry and things like that. So we've got a point on the curve of y equals the square root of x. So we've got the square root function that looks like this. And it says what point on that curve is the closest to 3, 0. So 1, 2, 3, right here. We want to find out what point is the closest. Okay. Well, if this point right here is 3, 0, and a point on the curve right here is x, y, I want to know when is that distance the shortest so that point on the curve can be the closest to 3, 0. Okay, now there are some problems like this in the 1050 book that they use here at the community college, and this is what it's based on. Let's think about the distance formula. How do we find the distance between 2 points? Well, it's that big square root and then what? It's the difference based on the Pythagorean theorem. It's the difference in the x coordinates, so it's x1 minus x2 quantity squared plus y2, whoops, sorry. I did x, let me do the 2's because we typically see them that way. Okay. And then it doesn't really matter here, y2 minus y1 quantity squared. Because what you're going to do is you're going to find the difference between the x coordinates, square that, that's always going to be positive. Difference between the y coordinates, square that, that's always going to be positive. Okay? So let's call this x1, y1, and let's call this x2, y2. Now, if I just blindly go through and plug those things in, this is going to be x minus 3 quantity squared. This is going to be y minus 0 quantity squared. And at this point, something should really be bugging us that we've mentioned before. What don't we like about this? It's got 2 variables. Well, what one would we like to replace? Let's replace the y. What does y equal? Yeah. If you know x, you know the square root of x. You know what the y coordinate would be. So we're going to take this and we're going to change this, and I'm going to emphasize that we've made this a function of x now. So this is going to be x minus 3 quantity squared. This is going to be the square root of x minus 0 quantity squared. Here's our distance function. So any function on that curve, any point on that curve, we can find the distance between that point and this point 3, 0 using this little function right here. So let's clean this up just a little bit. This is going to be the distance equals big square root. This is going to be x minus 3 quantity squared plus, this is just a plain old x, isn't it? And what do we want to do with this function? Minimize. So we want to minimize this right here. Now, that means we need to, we need to consider the domain. What would the domain be? What's the smallest x can be on the square root function? 0. What's the largest it could be? That could be infinity, okay? So maybe the minimum is at 0. Can you just look at it until it's not? Okay, if x is 0, I'm at this point right here. That's 3 units of distance. If I just slide up here just a little bit, I mean, clearly I've gotten closer, right? Okay, so we want to minimize that. It's not going to be at the end points. We've got one on this end. We don't have one at the other end. Okay, we want to find where the derivative equals 0 and where the derivative doesn't exist. But let's be smart about this. Do you want to do calculus on this big square root with a quadratic underneath it? Couldn't we minimize this entire function right here by minimizing this? Couldn't we just minimize y equals x minus 3 quantity squared plus x? If you minimize the radicand, haven't you minimized the radical? If you minimize what's underneath the square root, haven't you minimized the square root of what's underneath it? Does that make sense? So I can find the minimum of this right here, and let's think about this for just a second. I'm going to come up here and I'm going to change colors. This would be y equals x squared minus 6x plus 9 plus x. So this would be y equals x squared minus 5x plus 9. What shape is that if we were to graph it? Parabola. Which way does it open? Opens up. So it has a minimum at the vertex. Remember that formula that allows you to find the x-coordinate of the vertex? Negative b over 2a. You want to see something interesting? What if I wrote a general quadratic this way? And what if I found the derivative? And what if I wanted to know where the derivative equals 0? So in other words, where does this parabola level off for just a second? I'd want to know where it equals 0, right? So this would be when 2ax equals negative b, or in other words, when x equals negative b over 2a. Well, that's not how we got it, but isn't it interesting? The way you got it in your pre-calculus classes was completing the square on the quadratic. The way we find it here is find the derivative of a general quadratic and set the derivative equal to 0. You still get negative b over 2a. Isn't it amazing how all that stuff fits together? Okay. Now, I'm not going to finish that problem. That one's easy enough. Well, my gosh, you've got it finished already. You know what the x-coordinate is. Plug it in and find the y-coordinate. Okay. So be smart about how you do those. Okay, this problem is number 35. Okay, and I have a slight problem with the wording of this question. This is right out of the textbook. In fact, I think it's one on your assignment, although I'm not sure. It says a piece of wire 10 meters long is cut into 2 pieces. One piece is bent into a square, the other into an equilateral triangle. How should the wire be cut so that the total area enclosed will be both a minimum and a maximum? So we want to find the total area enclosed if we take a 10-meter long wire, cut it in 2 pieces, shape one in a square and the other one in an equilateral triangle. Okay? So again, a completely contrived problem, unless you were some artist or had some really interesting manufacturing requirement. You probably wouldn't do this, but at least we can use some familiar ideas here. So here's what we've got. I've got a 10-meter long wire. So from here to here, it's 10 meters. And I'm going to make a cut in it so that I've got 2 pieces. Let's say this piece right here is x, and I'm going to use that to form the square. And let's say this piece right here is what's left over to form the equilateral triangle. So what's left over? Okay, so this is going to be 10 minus x. So we're going to make the square out of this, and we're going to make the equilateral triangle out of this. With me there? Okay. Well, the square is pretty easy. If it's x units all the way around, how long is each one of the sides? Okay, each one of them is going to be x over 4. We're going to take that length, we're going to divide it by 4, and we're going to make a square out of it. Okay, all 4 of those sides have to be equal in length. Okay, that means the area of that square is going to be x squared over 16. So the area of the square, I'll call that a sub s. Any questions? Okay, let's talk about the triangle now. All the sides are the same. Equilateral triangle. So how long is each one of the sides? 10 minus x over 3. 10 minus x over 3. And this whole side right here is 10 minus x over 3, right? Okay, how do I find the area of a triangle? Okay, 1/2 the base times the height. Okay, now, what's the base? 10 minus x over 3, right? Okay, but I need to know how tall it is. So I'm going to change colors here so we can focus on this calculation right there. I need to know how tall this is. Ideas? How would we use the Pythagorean theorem? Okay, so here's the idea. Drop this straight down. This is an equilateral triangle, right? So that means this side right here, so let me erase this right here. This side right here would be 10 minus x over 6. So from here to here is 10 minus x over 6. And then I want to figure out this one right here. I could use the Pythagorean theorem using this side and figure out what that side is right there. Or, very good. It's a 30, 60, 90. So how do I go from the short leg to the long leg on a 30, 60, 90? Oh, see, your geometry teachers would be really disappointed. Yeah. Okay. So let's just make sure we're clear here. Special right triangles, they never go away. If this is x, the hypotenuse is double x, and the long leg is x radical 3. That's on a 30, 60, 90. On a 45, 45, 90, if this is x, that's x, and this is x radical 2. Okay? So just keep those in mind. So what that means is h on this problem would be a radical 3 times 10 minus x over 6. So that's what I'm going to put in here for the height. So this is going to be radical 3, 10 minus x over 6. Any questions? Okay. So I've got the square right here, and I've got the triangle right here. And what I want is a formula that figures out what's the total area, what's the sum of those areas. So the area as a function of x is going to be the square, x squared over 16, plus, let's see what we've got here. I've got a radical 3 on the top, and I've got a 36 on the bottom. And then I've got, let's be smart about this, 10 minus x, quantity squared. And you just want to find the maximum and minimum of that. Okay, now, here's where the wording becomes important. What's the domain for this? What's the smallest x could be? Okay, so we could start right here, right? And what's the largest x could be? Okay, the way the question is worded, it says it's cut into 2 pieces. It says you definitely cut it into 2 pieces. Okay? Now, the way they've interpreted this in the back of the book is they've interpreted this as, you know what? Under this scenario, get me the maximum area enclosed. I don't care if we have 2 pieces. So they've actually used 0 for the smallest x could be and 10 for the largest x could be. So if x was 0, we've put all of our area in the triangle. If x is 10, we've put all of our area in the square. Okay? So along with finding where this derivative equals 0, okay, which if you look at this right here, isn't it going to be a quadratic? And aren't quadratics pretty easy to find where they equal 0? Okay? All right. So I'll leave that to you to do. If you had to take a guess, which is the most efficient shape? Square is probably the most efficient shape. So you're probably going to get the most area when you make it all out of the square. No, because not every one of them is 10. Okay, be 2.5 squared. Okay, so I'll leave that for you to finish, but that's how you set up the problem. From there, it's just finding the derivative, setting it equal to 0, or if you even wanted to find, well, on a test, I'd want to see the derivative. Okay, if you want to double check it using some pre-calculus knowledge, that's fine with me. Okay, any questions? Okay. Let's see. If we've got time, we'll come back and do this one, but let's take a look at this one. This is an example out of your textbook, so this is a very interesting application. It's very interesting from a discussion standpoint. I'll set you at ease right now because there's a lot of talking right there, and if you read that question, there are a whole bunch of words in there that are like, that sounds really interesting if I was a finance or business major, but I'm not quite too sure what they're after here. Okay, but this is an interesting problem for discussion's sake. So in chapter 3, we learned that the marginal cost function was the blank of the cost function. Whenever we hear the word marginal, we're talking about the derivative of that function. So it's the derivative of the cost function. Okay. The problem with dwelling too much on cost, say we want to minimize cost or maximize cost or whatever it happens to be. Okay. The problem with dwelling on cost is that's not the whole picture when we're in a business situation. Okay. And neither is revenue. Okay. What we're really after is we're after profit. Because if you don't have very much revenue, but your cost is very, very low, you're still making a profit. Okay? If your revenue is really high, but your costs are even higher, you're still in the hole. You're not making any profit. Okay? So what we really want to talk about is profit. And in order to get there, we're going to take this a little bit of a piece at a time. This problem here is kind of interesting. We're going to figure out one tiny aspect of this type of scenario. Okay? So if we've got the revenue, marginal revenue would be the derivative of revenue. Okay? If we've got the profit function, marginal profit would be the derivative of profit, and so forth. Okay? So if X is the number of items that we sell, then R of X is the revenue produced by selling that many items. Okay? P of X is what we call the demand function, or sometimes you could call it the price function. Okay? You know that as supply goes up, demand usually falls and the price falls. Okay? So as supply goes up, the price falls because the demand falls. Okay? And vice versa. And C of X is the cost function. Okay, that means if we were going to figure out what the revenue was, how much money is generated when we sell X number of items, well, you take the number of items and multiply it by the price. If you want to know how much revenue you've produced, how many did you sell, and how much did you sell them for? Just those two things will produce the revenue. Okay? Then the profit, notice this is a capital P. The profit is going to be the revenue minus the cost. So take how much you brought in, subtract how much it cost you to produce those items, and that'll tell you what the profit is. Let me make that look right there. Okay. So if we make a little substitution, this would tell us that the profit is the revenue, which is X times the price, minus whatever the cost of those X items were. Okay. So again, by the same token as we talked about previously, marginal revenue is also the derivative of revenue, and marginal profit is the derivative of profit. Okay? So this is, even though when I read this, this isn't going to sound very simple. I mean, maybe you're better at conceptualizing these than I am, but the first time I saw problems like this, it was like, that's going to take a little while to think through. So here's what we've got. A store has been selling 200 Blu-ray disc players a week at $350 each. A market survey indicates that for each $10 rebate offered to the buyers, so each $10 reduction in price, the number of units sold will increase by 20 per week. So if we drop the price, we're not selling each item for as much, but we're going to sell more of them. So that's part of the business world that might be a little bit counterintuitive. If you lower your price, sometimes you can actually make more money because more people come in and buy it. Lower the price, the demand goes up. Okay? All right, so it says find the demand function. And again, another way you could think of the demand function is the price function. Okay? And the revenue function. How large a rebate should the store offer to maximize revenue? How large a rebate should the store offer to maximize revenue? Okay, so this is what we've got to figure out first. It says find the demand function and the revenue function. So let's focus on this right here. Let's find the demand function or the price function P of X. What is the price based on how many we sell? So let's think about what we've got going on here. And it has a hint there. It says, notice that the price will fall in a linear fashion. Every time we lower the price by $10, we're going to sell 20 more units. Okay? So we've got price up here, and we've got units down here. Now, this is falling in a linear fashion. The price is going down $10 for every 20 units increase in sales. Slope's going to be negative. Okay? And it's linear. So what things do we need to write the equation of a line? Okay? So we need a point and we need a slope. So I need a point on this price X. What is it? Okay, 200 Blu-rays, $350 each. Okay, so our point right here is 200 Blu-rays at $3.50 a piece. So there's our point right here. Now what's going to happen is every time I lower the price by $10 through a rebate, I'm going to sell 20 more units. So if I go down $10, I'm going to sell 20 more units. So there's my slope. Slope is negative 10 over 20, so negative 1/2. So the slope is negative 1/2, and the point is 200, 350. So here's our demand function, our P of x. P of x is going to be, let's see, if we wrote that in point slope form, slope intercept, however you want to do that, it's going to be the slope. So if here's what I'm thinking of. So this is going to be x minus 350, or sorry, 200. And then if I slide that over to the other side, that's going to be plus 350. So here's P of x. Negative 1/2 x. And then if I distribute through, I get, this is going to be plus 100, and that's going to be 450. That, I think, is the hardest part of the problem. Okay, let's talk about this for just a second. This is a fairly simplified example again, but there's something we can learn about this. Okay, what is that 450? It's the y-interceptor on this one. It's the price intercept. Weston? So if you were to put that price at 450, you get zero what? 0 units sold. Okay. If you sell your Blu-ray DVD players at 450, nobody's going to want them. What's your revenue then? 0. Okay. You're not selling anything, so you're not bringing in any money. Okay. And this is what business owners have to deal with all the time, because they'd like to make as much per unit as possible, but if they set the price too high, they're not making any money because none of them are going out the doors. Okay? There's no demand for their product at that price. Okay? So that's this extreme right here. Let me change colors. That's this extreme right here. If we hit this price point right here, if we sell it for 350, there are 200 of them going out the door every week. Well, let's make more of them go out the door. And more and more and more. Where would it hit over here? Okay, so what would happen there is if we offer it free, we're going to sell a ton of them, but again, we're not making any money because they're going out the door free. So somewhere in between, we want to find a balance between the two of those. It's very clear on this problem that the extremes on this demand function are not going to produce the maximum revenue. It's got to be somewhere in between. Does that make sense? Okay. Question? And so tell us about UTA. Yeah. What's a pass? Like 140?
What I saw online, it's like $85 a month. And I fill up my car with $20 worth of gas about every week.
Yeah. So real life example here, could UTA get more ridership and potentially more money if they lowered the price? Maybe. Okay. There are a lot of people that get on tracks without paying. Not buses though. Okay. Not buses. So do you think UTA has employed people to figure out where that price point ought to be? Yep. Probably. Did they get it right? Okay. According to Michelle, no. Okay, and I would agree based on what I've seen. I mean, I make a decision. If I want to go downtown, there are two things that factor into that. How much is it going to cost and how long is it going to take me? I don't live very far from a track station, but if it costs me $5 to get there and back, I think it's $2.50 each way now, isn't it? If you ride tracks, okay, that's a gallon and a half of gas. I can get down there and back for a gallon and a half of gas. Okay, and I can do it a little bit quicker. So now, if it was $2, would I be willing to take a little bit more time to ride tracks and save a little bit of money? Probably. So there are lots of things that enter into that. So the point here is great discussion. Okay, business, economic, stuff like that. There are lots of things that go into that and lots of things where we consider we want to maximize ridership. We want to minimize our cost. Okay, we want to maximize our revenue and maximize our profit and things like that. Lots of decisions have to be made to do that. And if you know the math behind it and can come up with a function like this, you're probably going to be better off in making those decisions. Okay, does that make sense? Okay, so that's the hardest part of the problem. Then it says, let's see, how large a rebate should the store offer to maximize revenue? But I ignored this part right here. Revenue function. Okay, what's the revenue function? How many you sell times the price? Do we have the price? We've got our price slash demand function right here. How many do we sell? That's represented by X. So R of X is going to be the number we sell times negative 1/2 X plus 450. Okay, now, do we have a domain for this? Do we have a domain for X? 0 and free. We'd have to find what that intercept is right there. Conceptually, do we need to worry about this? We don't, okay? Because we already talked about what happens at the extremes, okay? Yeah, I think it would be 9. Yes, it would be 900. Yep. Okay. So fathom that. This is where sometimes the math breaks down just a little bit. Seriously, if you were giving away free DVD players, this predicts that only 900 people would come into your store.
Well, you only had 900 in the store.
Okay, we'll take that. All right. Only 900 in the store, or you live in like Firth, Idaho, where there's only 900 people. Okay. So what do we want to know from this? Find the derivative, find the maximum, find the derivative, set it equal to 0. Okay. We don't have to worry about this not existing anywhere because it's just a nice little polynomial. So minus 1/2 X squared plus 450. X, thank you very much. Good. Find the derivative, negative X plus 450. So X equals 450. So what do you do with that? Okay, does that answer the question? How large a rebate? That doesn't answer the question. That says, in order to maximize the revenue, we want to sell 450 of them, smack dab in the middle between 0 and the 900. So we want to sell 450 of them. So the question is, if you want to sell 450 of them, what price do you need? Well, if you're only selling 200 of them now at 350, you've got to lower your price to get more people to buy them. How much do we need to lower our price? Well, let's come back here to our demand function. If you want to sell 450 of them, put it in there and it'll tell you what the price is. So this is going to be P of 450 is going to be negative 1/2 times 450 plus 450. So that's going to be minus 225 plus 450. So that means 250. Or sorry, 225. 225. So P of 450 is, now 225, there are lots of numbers rolling around here that are in the hundreds. What does that 225 mean? Okay, that is the price. That's how much you should sell them for. Okay? So the way this question is worded, it's a little bit, it's a little bit confusing because we're talking about offering rebates. Okay, effectively we're lowering the price. So we want to lower the price from 350 to 225. So we want the price to go down $125. So we need to offer a $125 rebate and we'll maximize our profit. Think about that for just a second. We're going to cut the price by more than 1/3 and we're still going to make more money. Cut the price by more than 1/3 and you still make more money, okay? At least more revenue, okay? We'll assume that the profit goes up in the same fashion, yeah.
So I think that when they do mail-in rebates, some people forget to do it, and other people do it correctly. So, you know,
So Juan brings up a good point. Do you think companies have thought of that? That there's a lack of follow through or proper follow through on rebates? Absolutely. So if you walk in there and it says, okay, this is a $350 item, but if I do the rebate, I get $125 back. You think that's a big bite? Yeah. Okay. And is there a certain percentage where they don't have to pay the rebate and they actually make 350? Absolutely. Okay. They do the math on that. They probably know a very good percentage of how many people are not going to actually get that rebate. So they made 350. Okay. So they've increased their revenue even more by that lack of proper follow through. Okay. Very interesting. Any other comments about that? Okay. Any business period is tricky. Yeah. Okay. Any questions? Okay. All right. That's all I've got for this one right here.